It's a great privilege to speak in this 50 years QCD celebration. And unfortunately, as I try to board the plane and I found I have COVID. And so, but I don't want to give up the chance for give a talk here because the likelihood of speaking in the 100-year celebration is very small. So I'm going to talk about a old subject, older than QCD itself, but also dirty. And so now it falls into the domain of nuclear physics. I try to bring some elegance to this topic. That is, how to compute a Feynman Parton distribution lattice through a large moment effective theory. So here's a plan of my talk. I will give some brief introduction. And in fact, most of which you probably can skip because this audience quite familiar with some of these topics. The main point I want to explain is the partons in Feynman's way is in fact an Euclidean formulation. And so therefore that one can actually construct an effective theory for partons, and by making large momentum expansion of quantities that can be calculable in Euclidean theory. And I will focus mostly on some of the applications for PDFs and GPDs. I can try to explain some of these jargons later. So we all know the Parton model is extremely useful, and it formed the basis for the explained high energy scattering. The essence of the Parton model is that, we talk about high energy scattering and particle travels at near speed of light. And the assumption of this is, of the Parton model, is that let's just consider travels at speed of light, or the momentum of the proton or hadrons is equal to infinity. And that brings us to the infinite momentum frame. And in this frame, the hadrons, the proton, can be considered as a collection of interaction-free particles, and which we call partons. And then we can count or do statistics on partons and according to its longitudinal momentum. And then they introduce the Parton distribution function or Parton density. The x is the fraction of momentum carried by the partons. Now, PDF is the bonded state property of the proton, and it's essential for explaining the results of high energy collisions. Typically, for example, in the LHC, that we look at the hadron-hadron collisions, and we write down the factorization theorem to write cross-section in terms of the Parton cross-section and convolute it with the Parton distributions. Now, what perturbation theory or asymptotic freedom allows to do is to calculate the Parton cross-sections. And so to get the theoretical prediction or standard model prediction, we need to know these Parton distributions. And so we basically so far took a phenomenological approach that we know some experimental data, and we calculate the Parton scattering, and then we try to extract the Parton distribution from the experimental data. And this has been extremely active and successful field, and many people worked on this and with different kinds of ideas, but they more or less come up to some convergence that what a Parton distribution look like in a proton. And so here I show a typical plot of the Parton distributions and from NNPDF. And these Parton, the phenomenological Parton distribution are essential for us to understand data from LHC and forms the standard model prediction and compare against the experimental data and hopefully to find some loopholes where the new physics lies. Now, Parton distribution for many years has been formulated as Lycon correlators. And so in the following few minutes, I'll try to explain why this has happened and why this led us to a very difficult situation. So in fact, the studying systems moving at the speed of light um, precedes the Parton model. And after Feynman and Flang introduced the infinite momentum frame, and then Weinberg in 1966 wrote a paper talk about a scalar quantum field theory, what happens for the dynamics of the theory, infinite momentum. And what he found was that the all kinematic infinities can be removed from the calculation and results a set of rules for perturbation theory formulated in an old-fashioned approach, which I call the Weinberg rules. Now, those rules are very similar to non-relativist theory. And this approach has been followed after Parton model was put forward and by many people. In particular, here I would like to mention a paper in 1969 by Chang and Ma, and consider QED at infinite momentum. And a similar paper by Kogan and Soper in 1970 on talking about QED in the infinite momentum frame. Now, an important and interesting discovery by Chang and Ma is that all Weinberg's rules in the infinite momentum limit can be obtained from quantize the field theory with the new coordinates, the x plus and the x minus, which two Lycon directions, once you have a direction of travel and speed of, and time. And so all you need to do is to treat the x plus as a new time and x plus as x minus a new space. And this, in fact, is what's called the Dirac form of dynamics. And so basically what they have found, the Weinberg's rules exactly corresponds to the Dirac's light-front dynamics proposed in 1949. And a paper which basically nobody paid any attention until that Cheng and Ma made the link. And if you look at the citations of Dirac's paper, virtually no citation before 1969, 1970. But right now there are some citations because of the connection with particles traveling at the speed of light. And this dynamics is the light front dynamics, and Stan going to talk about this more later. Now, we know in deep balance scattering, that was the context where partons were introduced. It was realized by many people at that time that process is dominated by Lycon correlators, Lycon correlations. So you look at the currents and the Lycon correlation dominates. Now, when Feynman introduced Parton models, the proton is made of many constituents. And we know the final partons, the word line is going along the Lycon direction. And so therefore, if you look at the right-hand side of this, and this is basically the word line of a quark or parton and traveling in the final state. And that's where the Lycon correlation or Lycon correlation come from. And so therefore, that if the lifelong correlation is captured in the lifelong quantization, and so therefore it is very natural to interpret the Feynman's Parton as fork components in lifelong wave functions. So therefore, if we quantize a theory and in a lifelong and construct the proton's wave function with creation annihilation operators, and then you can calculate simply the parton density as the number density in a wave function, and stand a lot of work in this area, and wrote a very popular review paper. But it turns out it's quite difficult to solve light-from wave functions, even though you can quantize the theory, but it's still a strong coupling problem. And there's no demonstration that one actually can do weak coupling expansion. And in fact, Kim Wilson wrote a paper in 1994 with a bunch of collaborators and hope that the some kind of weak coupling expansion exists, and so therefore you can compute the light from the wave function, and from which you can calculate parton densities. But I think that the progress in that direction is very, very small after nearly 30 years. And there are various other reasons why light from quantization directly solving QCD has been very difficult. One reason that why the parton theory is difficult is because that the correlation length as the momentum goes to infinity actually goes to infinity. We know the PDF at a small x behaves like x to the minus alpha when you go to position space, and this corresponding to a correlation function along light cone goes like to some lambda to the alpha minus 1. So the correlation length corresponding to this correlation function is actually going to infinity. And so therefore that in some sense, if you look at the parton or proton moving with infinite momentum, and we're dealing with a system with infinite correlation lengths. At least that's the case in the longitudinal direction. Now, of course, that if you look at the standard particle theory textbooks, the language to formulate parton physics actually is in terms of effective fields called collinear modes. So you have for example, a quark, and with coordinates, the n here is the light cone direction. And so you have fields which are essentially, most important component which lie along the light cone directions. And so therefore the parton physics formulated in terms of these fields are light cone correlation functions. So for example, if you look at the soft collinear effective theory, where the parton density shows up, there are light cone correlation functions, light cone correlator of fields. So therefore, if I draw the space-time picture here, so the dots here represents a bunch of fields which are distributed along the light cone directions. Now, the beauty of this formulation, that is the parton physics in terms of light cone correlation, is that it's independent of hadron momentum. And it can be calculated in any hadron momentum states. In particular, they can be calculated in the rest frame. And so that's a beauty of this either lifelong quantization or light cone correlation functions. Now, if the parton density is a lifelong correlation, which means that we have to deal, if we want to calculate this, you have to deal with real time. And we know that the Monte Carlo simulation with real time is a no-go, and because of the rapid oscillating phase factor. And the signals are usually exponentially small. But people have been thinking about using a quantum computer to solve these kind of sign problems. So in fact, there is a small community of people think about calculating Parton distributions using a quantum computer. Now, here I would like to rewind the clock, basically, going back to Feynman partons and argue that the partons actually can be formulated in a Euclidean way, completely independent of time. So if you think about the origin of the Parton model, which again come from deep lines of scattering, and which in fact is a generalization of electron scattering in non-relativistic systems. Okay, for example, electron scattering atoms or scattering in the condensed matter systems, neutron scattering in liquid helium, etc. So for non-relativist systems, if you study those scattering processes, the key quantity is called the momentum distribution of a quantum many-body system. So if you know the wave function or quantum many-body wave function of a system, you just need to Fourier transform. You know, if you got one particle, you Fourier transform, and the density, the momentum density is just related to the wave function in momentum space squared. And if you look at this in coordinate space, and it's just an equal time correlator in coordinate space. So therefore, the momentum distribution in the quantum many-body system, the Euclidean correlators are independent of time. And those quantities are generally amenable for Monte Carlo simulations. Now, so what is the difference between relativistic and non-relativistic systems? In the non-relativistic case, we know the system mass is or probe mass is large, and so therefore energy transfer is very small. So if we look at the deep elastic scattering in a frame in which the momentum transfer is very small, that is called the Biot frame, and in which the virtual photon energy is equal to 0. So therefore, you can go to a frame in which the virtual photon momentum, it just only has the space component, have no time component. In such a frame, that you're probing the momentum distributions. And this is the frame which, if you look at the momentum of the hadron, it's actually proportional to the Q. And so therefore, in the BR10 limit, the momentum of the hadron goes to infinity. And so therefore, the Parton distribution is nothing but a momentum distribution for a hadron moving at infinite momentum, which is exactly what Feynman said in the Feynman Parton model. So we can start to consider momentum distribution in a hadron state with some center mass momentum P. And because of relativity, the momentum distribution now depends on the momentum of the hadron. And the momentum K here is some constituents, you know, a upward or a gluon. So you got a momentum density, which depends on the momentum of the hadron or center mass velocity. And of course, in high energy scattering, we're only interested in longitudinal momentum, and so therefore we can integrate out the transverse momentum. And the PDF, in Feynman's view, is just the limit of this quantity as the momentum of the hadron goes to infinity. So that gives you the PDF. So the PDF is the momentum distribution as the system's momentum is going to infinity. Or if I have coordinate space correlator, all I need to calculate is the equal time correlator in a frame in which the momentum of the hadron is equal to infinity, and I Fourier transform this correlator that will give me the Parton distribution functions. Okay. So let me know if there's 5 minutes left. I don't want to. Okay. So I'm going to skip this. The relation between two Parton formulas, and of course, it's just a Lorentz transformation, but it's an infinite Lorentz transformation. Now, this picture of the Parton distribution would allow us to do a large momentum expansion. Because directly computing momentum equal to infinity is very difficult. So therefore, we could consider calculated momentum density in the limit of p is equal to infinity. Now, the question, of course, is whether this limit is analytic or not. In other words, the quantity you calculate, does it have a p is equal to infinity limit? And if it is analytic, that is, this limit exists, then we can do a Taylor expansion for the momentum density. As in terms of large PZ, the expansion parameter will be m divided by PZ squared. M is some kind of bound state scale. And the leading term Fx is the Parton distribution we're after. And so this expansion is kind of interesting because it allows us to calculate the Parton distribution from the momentum distribution of a Parton in a hadron, but with moderate PZ, so long as this expansion parameter is small. So if I make a very naive and optimistic estimate, is that we know the hadron scale is in the order of 1 GeV. Suppose I have a hadron equal to 2 GeV, then the expansion parameter is a quarter. And a quarter is smaller than with a third, and the third is the large NC expansion people use in QCD. So it's not a bad expansion parameter. And we do this all the time because in lattice, we know the UV cutoff is equal to infinity, but we're going to expand stuff into the A lattice spacing if a point 1 Fermi, and we're expanding around. We're using 2 GeV to approximate the UV cutoff equal to infinity. And the same thing happens with the HQET. And we can apply some heavy quark expansion for some quarks with mass around a couple of GeV. So before one gets a little too far, we have to discuss a problem in quantum field theory, that is the UV cutoff. So when you calculate the momentum density, and that's going to also depend on UV cutoff. And because of QCD has non-trivial UV behavior, it turns out this momentum density is not analytic at PZ equal to infinity. And specifically, it depends on how do you take the limit of PZ equal to infinity. And you can let PZ much smaller than the UV cutoff and let both go to infinity. And this is the limit where you can do lattice QCD calculations. On the other hand, you can also let the PZ much greater than lambda QCD or the UV cutoff. This sounds like an unphysical limit, but that's exactly what high energy Parton distribution is defined. So this is the Parton distribution limit. Now, what lattice can calculate is a limit 1, and what we wanted is the Parton distribution is the limit 2. And so therefore, how can you recover one from the other? The answer is matching in effective field theory. And so the point is that because of the non-analyticity, you're going to have logarithms of the PZ And so logarithm of PZ, you can not take the PZ go to infinity directly, but it can appear as a coefficient function in front of the F. So if you use the effective field theory philosophy, is that you can calculate a momentum density on lattice with PZ much less than the UV cutoff, which is the lattice spacing. And then you can match this quantity to the PDF, which is the other limit when PZ is much greater than lattice scale, because the switch of the limit is only involves the high momentum physics. So therefore, that's potentially calculable. And so that's, these Z factors. So Z contains all the perturbative contributions with a larger logarithm PZ, and that accounts for the effects of the switch of the two limits. And this expansion is only good if PZ is very large. So if you do detailed examination, you discover that the scale which appears in the denominator is not the momentum of the hadron, but the momentum of the partons, the active parton and inactive partons, both scales appears in here. And so therefore, which means that when one of the parton fraction gets very small, the expansion breaks down, and it makes theory hard to calculate. So this is the content of the large momentum effective theory. I'm going to skip the momentum renormalization group equation because this gives you another interpretation what the de Graaff evolution means. The de Graaff evolution usually is interpreted as a transverse momentum evolution, but in this context, the de Graaff evolution actually is related to the longitudinal momentum evolution. I do want to talk about the universality because when you calculate the parton distribution, you started with an operator as an equal time correlator, but that operator can be of many different types. In fact, there are infinite number of ways I can choose operators. In a large momentum limit, it produces the same results. And so that's the universality, okay? But which operator you're going to try to use to calculate, it's a matter of a hit and miss. So you just need to choose one and calculate and choose a different one to see how the rate of PZ go to, get large. You're going to converge into the parton limit. So in the rest of, let's see, I have about 11 minutes. I can talk about a few applications very quickly, flash through. One is the gluon total helicity, and polarized Rick, in fact, was in fact motivated by trying to measure the total gluon helicity in a polarized proton. And if you look at the PCD definition of delta G, it's a very complicated light correlation function of gauge invariant fields. And that's very difficult to calculate. However, in Limit setup, one can start it with a local operator E cross A, which is gauge dependent. But so long as they choose a physical gauge, and you calculate it in a boosted hadron, and as the momentum of the hadron goes to infinity, that all the gauge dependency disappears, and you recover the delta G, the helicity. And this is essentially the Weizsäcker-Williams picture. And so the conductor lattice group, in fact, used our idea and did first calculation. They calculated in Coulomb gauge and tried to look at this as a function of hadron momentum. As you can see, that the error bar is quite large and haven't connected with the momentum evolution equation yet. So I'm going to spend a few minutes to talk about the PDF and which motivated this calculation. Okay. So what you can do, you can start it with a equal time Euclidean correlators and in a larger momentum state. And you want to start with something here with a gauge invariant, and so therefore you want to have a straight line Wilson length. So this has been called a quasi-PDF in the literature. So you can use this and compute a large momentum. So this was calculated in Parton by BNL and collaboration. So this is the Parton distributions showing as here, I think in the red band is what this lattice calculation give you with a pion moving at a couple of GeV momentum. And as I said, the larger movement, the expansion breaks down at a very small x, very large x, but the intermediate regions is calculable. Now, I have to apologize that I haven't, discussed the other approaches people want to calculate on lattice and try to get the Parton distributions. But lemma is the only way you can calculate the x dependence directly and without doing, phenomenological fits. And that is what I like, because the field theory should predict the x dependence, not through the fitting. And so here is an example of the universality study. And Yon from Aga National Lab also studied, apart from this standard quasi PDF correlator, they consider simply side-by-side correlator in Coulomb gauge. And so they wanted to go to large momentum and do the matching and compare with this gauge invariant form. And then they found that when the momentum gets pretty large, like 2 GeV or so, the results are very similar. So that's a demonstration of universality. So here I show you a calculation was unpublished by LPC collaboration. The proton U minus D. The dashed curves are fits from high energy experimental data. The red curve here is actually kind of semi-final results. Still, some work need to be done to give the error bar and etc. But the error bar is not huge. But you can see that X dependence is completely predicted by lattice calculations and matching. Let me see my time probably. I still have 5 minutes, I hope. Is that right? Okay. Okay, so let me talk about the generalized Parton distributions. A quantity which was introduced in the mid-1990s. Basically, apart from looking at the longitudinal momentum distribution, that we're also interested in the transverse coordinate space distributions. And so therefore it allows you to construct the angular momentum of the partons. There are experimental processes to measure these quantities. And one of the first process that I proposed is called a deeply virtual Compton scattering, and in which you have the deep elastic scattering, but not looking at complicated final state. The final state is a diffractive state with a very high energy gamma and with a recoil of proton. And then Jian Wei is going to talk about a set of other processes try to measure these quantities with meson productions. Now, the lattice calculation presents no new difficulty because here you're looking at a transition matrix element of this operator. And so therefore initial final states have a different momentum. And so many people have proceeded to calculate this on Lattice. This is a paper published by Feynman Ling from MSU. And you can turn the lattice calculation into a picture for Parton distribution in coordinate space. So if you look at the three plots in the lower half of the slides, and this is x equal to 0.3. So you look at the x equal to 0.3 partons to see how they're distributed in the transverse plane. And likewise, you can do it for x.5 and x.7. So this GPDs will give you interesting pictures of parton distributions in 3D. The application 4 is the transverse moment dependent PDFs, which is a straightforward generalization of the Feynman's PDF, except now you're going to also looking at the transverse momentum. There are experimental processes. By the way, there's a very big book, TMD handbook. Many people contributed, for working on for quite a few years, summarizes the state of the field. Important thing is that this quantity is measurable, for example, in semi-inclusive deep elastic scattering. And so this distribution appears as non-particular quantities in the cross sections, which you can try to extract if the experimental data are available. And so one can construct the quasi-TMDs. By the way, these slides are from Yong Chao from the Argonne National Lab. And it has a comprehensive list of references. So here you can construct the quasi-TMDs and try to expand and enlarge momentum limit. And it related to the experimentally measurable TMD PDFs. And then you have perturbably calculable coefficient function, which is a C. And then gamma here is a quantity called Collins super evolution curve. And it's non-perturbative. And in fact, this quantity can also be calculated using large momentum effective theory, which I'm going to show you. So I'm not going to go to detail of these things, but to show you this Collins superkernel, which first computed by MIT group, and you can see that the kernel as a function of the impact parameter B, there are experimental extractions shown as continuous curves, and there are also the lattice calculations shown as dots. And as time goes on, the error bar is getting smaller and smaller from lattice QCD. So a real comparison between theory and lattice theory and experiment becomes possible. An important quantity appears in the factorization is so-called reduced soft factor, which can also be calculated using large momentum effective theory. I'm not going to go into. And finally, that combine all these elements, you can calculate the TMD PDF from Lattice. Okay, so finally, light front wave functions. I mentioned that the holy grail of light front quantization are those light front wave functions of hadrons. It would be nice to get all these wave functions and so you can calculate everything. But as I said, the direct solving light front wave function from QCD is extremely difficult. However, it can be obtained from the Lamette theory through matching and calculations on Lattice. And so here I show you one of the results for meson contains two Fox component or two Fox particles. And you can look at the wave function amplitude. It contains both real and imaginary part. And the left is real and right hand side is imaginary. And so the horizontal axis is X, and then the different colored band corresponding to different impact parameter. And so therefore, if we so it gives you if you Fourier transform this impact parameter, you would get transverse momentum. So therefore, you would have a transverse momentum distribution in a wave function. And so here showing you the wave function amplitude at x equal to 0.5 as a function of transverse space. And the shaded curve here shows some kind of models people have been used in the past for making predictions in the QCD factorization calculations. And the error bars are large, and there's a lot of systematic uncertainty has not been taken into account. But this is one of the first calculations, and so therefore, I hope in the future this can be improved considerably. So that's come to the end of my talk. And so basically, I try to explain that the part time can be calculated on lattice using large momentum expansion. So long as the momentum is much bigger than the hadron mass scale. And of course, creating a large momentum states on lattice is extreme challenge. And so right now, most of the people can only calculate with momentum of 2 or 3 GeVs. It will be very, very interesting that if we can push to 5 GeV, and then that a lot of systematics would be much suppressed. But nonetheless, that the third generation of calculation, I believe, for some of the quantities can reach 5% level of precision by improving the non-particular renormalization and two-loop matching and threshold resummation, Chris-Reed renormal corrections, etc. There's no obstacle other than probably the computational resources that we cannot reach higher precision in the future because, as I said, QCD is a theory which is fundamental, will be with us 100 years from now and 200 years from now. So I think that we can always try to do better job in the future. Okay, thank you very much.
Okay, thank you, Xiangdong. We have time for a few questions.
Good to see you remotely. I'm sorry about your illness, Xiangdong. Can you hear me all right? Yes. So it's important to emphasize that what we're talking about in light front theory is the light front Hamiltonian. The formalism is completely frame independent. There's no boosting of momentum. You're using light front time, which is the time that that experimentalist uses to measure apparatus, a hadron. The light front wave functions define the form factors. The light front wave functions define the structure functions. They obey all the evolution equations. The distribution amplitudes are the answers for the exclusive processes. And the challenge is to compute them, as you said, non-perturbably. So I respect that you're using the lattice method. However, an alternative method is matrix diagonalization. That was very successfully used by Hornbostel to solve basically any 1+1 quantum field theory, Schwinger model, to Hoof model. But nowadays, actually, and I'm going to talk about this today, is a brand new method, non-perturbed method, which is based on ADS-CFT correspondence. It's called light front holography. And the results are rather remarkable. You get out the spectroscopy of hadrons just from diagonalizing the light front Hamiltonian, just solving the light front Schrödinger equation. And you get also all the structure functions and distributions amplitudes associated with the complete hadron spectrum. So I'm really astounded by the successes of this new approach called light front holography. So if you can hear my talk later today at 5 o'clock, I'll explain that.
I appreciate your comments, Stan, and I agree with many of the things you said. The only question I have, it would be nice to use this method to solve 3+1 QCD.
Yes, of course. I'm going to talk about that specifically today using light front holography, of course. And it gives exactly predictions which agree not only with the eigenvalues of the light front Hamiltonian, but with the eigenfunctions, that is the light front wave functions. It agrees with phenomenology, just measure distribution amplitudes, structure functions, all sorts of phenomenology. There's now a huge industry in this field. I can't cover it all, but there's many, many applications.
Okay, thank you.
So people on the Zoom, anybody have questions? Do we have a question here?
Just a practical question. So how big lattice is and you should use, and what is the computer demand for it? So the volume dependence and the lattice side dependence, how do you, so you should have very large lattices to do that, or?
Right. It's kind of astonishing to see how fast people have making progress in doing a bigger and bigger volume simulations. When I was first involved in lattice calculation 20 years ago, people were talking about like 16 to the fourth. And in rare cases, people look 32. But now, it's pretty routine to use like 64 to the fourth power and tip to the fourth, and then also very small quark mass. And some of the simulation actually done at exactly the physical quark mass. So Lattice has made a huge progress in going towards the physical point. And the size effects, the lattice volume effects, can be studied in those calculations. I think at present time, those volume effects are quite small. They're much smaller than other systematics.